Now that we've studied comparable elements, we're going to delve in a little bit deeper and look at some concepts related to maximum and minimum elements in partially ordered sets. And again, another name for partially ordered sets is posets. Once again, we're going to review the definitions of partial orders and partially ordered sets. We're going to introduce some definitions related to partial orders and posets, and then we're going to give some examples. All right, so recall the important definitions that we looked at before. A is a set, R is a relation on the set A. We say that R is reflexive if every element is related to itself. We say R is antisymmetric if the only way we can have two elements be related in both directions is when they're equal. We say that R is transitive if whenever A is related to B and B is related to C, then A is related to C. And finally, a partial order is a relation that has all those properties. And any set that has a partial order on it is called a partially ordered set, also known as a poset. All right, so now I want you to think about the less than or equal to relation just on numbers, right? So A is related to B when A is less than or equal to B. So this relation orders all the real numbers from smaller to larger. And in general, we can imagine that our partial order puts elements in order from smaller to larger. So, or lower rank to higher rank if you prefer. So when we say A is related to B, we can think of A as being smaller than B, or A has a lower rank and B has the higher rank. So if R is a partial order on the set A, we say that X in A is a maximum element of A if B is related to X for all B in A. So this tells us that X has higher rank than every single element in the partially ordered set. Or another way of saying the same thing is that X is unambiguously the highest ranking element in A. We say that Y is the minimum element of A if Y is related to B for all B in A. Which also tells us that every element in A has a higher rank than Y. Another way of saying that is Y is unambiguous the lowest ranking element in A. So once you're able to say things are bigger or smaller or higher rank or lower rank, then you can start talking about things like minimum and maximum values. So let's see if we can apply this to a set, partially ordered set that we're already familiar with. So S is the set containing all the integers between 1 and 7, and A is just the power set, so it contains all subsets of S. So again, the relation that we use on this one is the subset relation, where X being a subset of Y means that every element of X is also an element of Y. So let's see if we can think about what a maximum element of A. This is going to be an element of A, so it's a subset of S that outranks every other element of A. So we want some subset T of S where X is a subset of T for all X in A. And if you do a little thinking about it, it looks like that maybe S is the one that we're looking for. S is a subset of itself, so it's an element of the power set. And it seems likely that all other subsets are going to be contained in that. Well, let's see, if we take any element of A, those are going to be subsets of S by definition, right? A is the power set of S, so it contains all subsets of S. But by saying they're all subsets of S, that says that S outranks every element of A. So X is a subset of S for all X in A, and that tells us that S is the maximum element. Now let's see if we can think about minimum element. So minimum element means some subset U of S, where U is a subset of X no matter what subset X that we have that's an element of A. And that says X is an A for all subsets X of S. And if you think about it for a little bit, it seems like the empty set is the one that we're looking for. Now, the nice thing about the empty set is it is a subset of every set that there is anywhere. In particular, it's a subset of all X where X is an A. In other words, all subsets of S. And that tells us that the empty set is the minimum element of our partially ordered set. So, as you might imagine, it is possible to have a partially ordered set where there's no maximum and no minimum. And the question then is there anything that might behave like a maximum or behave like a minimum in that partially ordered set? So we have a couple of definitions for this then. So if R is a partial order on the set A, we say that X is not maximum but maximal in A if there are no other elements B such that X is related to B. And what that tells us is that there are no elements that outrank X. We say that an element Y is minimal in A if there are no other elements B with B related to Y. In other words, Y is minimal when there aren't any other elements that Y itself outranks or have a lower rank than Y. Alright, so it seems like these are very similar to what we used to call maximum and minimum, but there are some subtle differences. First of all, an element being maximal does not imply that it is the highest ranking element. It may not be the highest ranking element, but what is true, it just says that no other element has a higher rank. Those are different statements. Being the highest rank means you outrank everybody. Being maximal just means that no element outranks you. And similarly, an element being minimal does not imply that it is the lowest ranking element. Lowest ranking means everybody outranks it. But minimal means that maybe not everybody outranks it, but nobody has a lower rank. So let's see if we can demonstrate these on a partially ordered set that's very similar to the last example we did, except we're going to remove a couple of possibilities. So we're still going to take the set S containing the integers 1 through 7. This time our partially ordered set is going to be almost all of the power set, but we're going to remove S. We're going to remove the empty set. In other words, we're going to remove that the maximum and minimum elements from our previous example to see what it does to this partially ordered set. It's still going to be a partially ordered set. It's just going to have different subsets that we're considering. So again, we're going to use the subset relation on A. That's going to be our relation. So what would a maximal element of A be? Remember, we can't choose the whole set S because that's not a part of our poset. Well, we want some subset T that is not a subset of any other subset of S. And you may stumble around for a lot of examples, but this one seems reasonable. I can't use the entire set S, but if I took one element out of it, say 7, and just included the numbers 1, 2, 3, 4, 5, and 6, maybe that might give us a maximal element. Well, let's see. We're going to try a proof by contradiction that T is maximal, which means we're going to assume that T is not maximal, which means there is some X in our poset, in other words, some subset X of S that is not S and not the empty set, with two things happening. T is a subset of X. X is higher ranked than T. And T is not equal to X. Because T is equal to X, of course T is a subset of itself. But we need something that has a higher rank. We're going to use this to prove a contradiction. And the key to this proof, and if you want more details, you should look in the reading, but the key to this proof is to show that either X is equal to T or X is equal to S. It's not as hard as it looks because remember, T and S are only one element away from each other. T has every element except for 7. S has all the elements including 7. And if you have more elements than all the subset just that doesn't include 7, that means 7 has to be included. So there's a pretty straightforward argument there. I'm not going to include all the details. But here's the problem. By assumption, T was not equal to X. Just go ahead and look at the bullet point a couple steps up. And we were assuming that S is not in A. So again, if you want some details of this proof, I encourage you to look at the reading. It's called Partial Orders and Partially Ordered Sets, and that one's on Blackboard. All right, so a couple observations about this, about maximal sets. This is the set T that we chose out, the numbers 1 through 6. That's not going to be the only maximal element of A. So this is a little bit weird to think about. But it turns out that if we did something like, oh, I don't know, T prime, which is all the set S with the number 6 removed, that turns out also to be maximal. And in fact, any subset of S that's only missing one element is going to be a maximal element. So you have tons of maximal elements for this poset. The other thing to keep in mind is T is not a maximum element. It does not outrank all the other elements in the poset. For instance, that T prime that we had in the bullet point just went up. T does not outrank that particular set, or any of the other maximal elements, right? Does not rank any of those. And not only that, but there's a lot of things that aren't maximal elements that it also doesn't outrank. Almost embarrassingly, if you just took the set containing 7, T does not outrank that. And the reason it does not rank that is because those two sets are not comparable. Remember, to be maximum, you have to outrank anybody. And to be outrank everybody, you have to be comparable with every element. So, just to summarize, maximum means definitely the highest ranking element, you outrank everybody. Maximal means, well, maybe you're not the highest ranking element, maybe you are, but maybe you're not, but no other element ranks higher than you. Alright, so let's play the same game with a minimal element of A. Now, sort of like before, we can't go to empty set as our minimal element because empty set is excluded from this partially ordered set. But we do want a subset U that does not contain any other subset of S. And if you, it probably doesn't take you much to think of an example. What if I just picked U to be a set that contains just one of the numbers, say the number 1? So let's see if we can give a proof by contradiction that U is minimal. It's going to be very similar to the one we had for the maximal elements. So we're going to assume it is minimal, or that it's not minimal, which means that there is some set that it outranks, right? So U is going to outrank this set. And what does that mean for you to outrank the set? That means the set X is a subset of U, but it can't be equal to U. And it can't be equal to the empty set. Then we use this to prove a contradiction. And the contradiction is, again, there's only one element between the empty set and the set U, right? The empty set has no elements. The set U just has one element. And so that means either X has to be the empty set, since it's contained in U, or it has to be U. There are no other possibilities. However, those are both excluded by our assumptions. We're assuming X is not the empty set because that's not in the post set, and we're assuming X is not equal to U because we need another set that it gets outranked by U. So again, I encourage you to look at the reading. It gives you more details of the proof. Again, it's called partial orders and partially ordered sets, which proves that the set U is a minimal element. So more observations, very similar to what we had with the maximal elements. As you may imagine, the set containing just the number 1 is not the only minimal element of A. If the set just contains the number 2, also minimal. And in fact, any subset just having one element is also going to be minimal. Exact same arguments. And U is not a minimum element. It is not the lowest ranking element. For instance, U and that U prime that just contains 2, the U prime does not outrank U, right? They're not even comparable, so it can't outrank them. And in fact, none of the other minimal elements can outrank U. And even a set that is pretty huge, at least in this context, the set containing every number except 1, doesn't even outrank U. And the reason why, I know you're not going to be surprised by this, it's because they're not comparable. In order to be outranked by something, it has to be comparable with it. So, similar summary as we had for maximal elements. Minimum means that it is definitely the lowest ranking element. Every element has a higher rank. Minimal means maybe not the lowest ranking element. Maybe not every other element has a higher rank, but no element has a lower rank. All right, so now that we finished this video, you're ready to do all the activities now. All the activities in partial orders directed graph, all the activities in partial orders divisible, and those are on the PDF files included with this video.